Hello everyone. Let's study about an important experiment done in physics called as Young's double slit experiment. It's called as YDSE in short. This experiment was performed by Thomas Young, and Thomas Young used a source of light. Double slit is a common experiment. Double slit basically means there are two openings. In some experiments, some scientists have used electrons or some other particle as a source. But here in this course, we are studying only about Young's double slit experiment where he used light as a source. Now, generally, what is done is you will have a monochromatic source of light. Monochromatic means single wavelength. So, we will have a source of light coming from an object, and then we'll have an opaque object placed in front of it, the small pinhole. So we have an opaque object with a small pinhole in it. Now this will give rise to spherical wavefront. These spherical wavefront would spread out in all directions, and in front of it we again have another opaque material with two openings. Now these openings could be small or big. They could be like pinholes or they could be like slit. Pinhole means a small opening, slit means a narrow opening. So basically we'll have two openings called as S1 and S2. Here S1 and S2 are at equal distance from the source S. The distance between source S to S1 S2 will be same. Now this hole here acts like a source. Even though we have a source somewhere far away, since we have a pinhole here, this acts like a source. So the interchangeable, even S acts like a source only. Now since this S1 S2 are again pinholes, even from here we get spherical wavefronts. Now these would expand and go away. We get a wavefront like this. We get spherical wavefronts, and then waves from these two would superimpose. Far away we have a screen. On the screen a pattern is formed called as alternate dark and bright bands as seen here. We'll look at few more diagrams to understand this. There's one example diagram shown here where we have a monochromatic source of light. It falls on a small opening. Here we have a slit from which spherical wavefronts are obtained. Again we have another opaque material with two openings. Each of this opening acts like a source. The reason that we want these two openings is because for interference to happen, at least we need two coherent sources. We learned in theory class that two independent sources can never be coherent. Therefore, what we do in this case is we take a single source of light and break it as two sources. So, for somebody seeing from this side, the slits S1 and S2 acts like two independent sources producing two coherent waves. Here is another view of the same thing. These are the patterns on the screen. As seen here, we get alternate dark and then bright bands. To understand in a better way, let's recall what happens in the experiment. In this case, at the center of the screen, let the distance between the two slits and this be capital D. At the center of the slits, somewhere from here, draw a line here. Then at the center, we get a bright band. This is called as constructive interference. That is because the waves from here travel the same distance. Let's draw a different diagram. This is a screen, and in front of it we have two openings, and this would be the center of the screen. Let's call this as point O. This is slit S1 and slit S2, and somewhere here we have source of light called as S. Now the waves traveling from here, the waves traveling from S2 will travel same distance. At this point S or the point O, they get a bright band. This is called as constructive interference. For some point P here, this point P would be bright or dark bands. Understand this, the waves from S1 would travel less distance than the waves from S2. So based on the path difference, for example, if S2P minus S1P, if this is equal to say n times lambda, n is equal to 0, 1, 2, etc., then this would give rise to constructive interference. For example, if the distance between S1P and S2P contains 8 lambda, that is, this distance contains 8 wavelength, and the distance between S2P and this distance contains, example, say 12 lambda, then the difference between S2P and S1P is 4 lambda. So this would give rise to constructive interference. To understand this, if we drop a perpendicular from this point onto the line S2P, called as point O, this distance we'll call as point Q. This distance S2Q is the extra distance traveled by the wave. In this case, it will be 4 lambda. Similarly, if we take a point somewhere here, say point P1, and if the distance between S1P and P1 is say 12 lambda, and distance between S2P and this, or S2 and this P is, for example, 17.5 lambda. In this case, the difference between this and this is 5.5 lambda. Recall that whenever it is 2n minus 1 lambda by 2, n is equal to 1, etc. In that case, if it's like 5.5 lambda, that would mean it is 11 lambda by 2. This would lead to destructive interference. So whether a given point is forming constructive interference or destructive interference depends on the extra distance traveled. Again, if you take some point from here, let's read our diagram. If we look at some point this side, say point P2, this is slit S1, this is slit S2. They could be slit or they could be even pinholes also. If we look at a wave coming from this point and a wave from here, then it is very obvious that the waves from S1 travel a larger distance. Suppose this distance here, from here to here, is say 4 lambda, and then from S1 to this point is say 7 lambda. In this case, difference of these two would be 3 lambda. 3 lambda is a multiple or is a form of n lambda. So at this point P2, we get a bright band. If we take another point somewhere here, a point P3, if this distance from here to here is something, if this is say 6 lambda, and distance from this to this distance is some value. Let's call this distance as say 9.5 lambda. In this case, the difference of 9.5 and 6 lambda would be 3.5 lambda, which is 7 lambda by 2. So this would give rise to destructive interference. Again, if we drop a normal from here, this would be the extra distance traveled. So whether a given point would be a bright spot or a dark spot or a bright band or a dark band depends on the extra distance traveled. That's called as the path length or the path difference. Based on that, we may get constructive or destructive interference. As given here, these are constructive spots. Or you can see here also, we get bright and then dark. We can understand same thing in terms of wavefronts also. That is, we have wavefronts drawn from a given source. Then these would give rise to wavefronts. So wavefront from here, wavefront from here, we can draw wavefronts from these points. Similarly, you can draw wavefronts from here also. Whenever the crest falls on crest, for example, the crest falls on crest, we'll put C comma C here. Crest falls on crest, or crest falls on crest here. Draw as crest falls on crest. In those spaces, we get constructive interference. When crest falls on trough, we get destructive interference. As seen in this diagram, these are points where crest falls on crest. Crest falls on crest. So if you draw the lines like this, so these would be points where we get constructive interference. So we can understand the same thing in terms of wavefronts also. Now what we'll do is we'll just read all the diagrams. Or we'll look at from here only. Let's call this as the center bright band, or I'll redraw this. I'll draw its front view. So here, this would be the center bright band. We get something of this kind. And then dark bands. Again, we get center. We get bright bands. And then dark bands like this. Again, like this, we get bright and then dark bands. I'm just drawing the bright bands. Here also we get similar kind of thing called as bright and then dark bands. It is not drawn uniformly here, but keep the idea that we get alternate bright and then dark bands. Get something of this kind. Alternate dark and bright band is drawn very big here. The idea is very similar. Suppose, let's assume that this is the central bright band. I'll just write it as CBB, and this is the central bright band. This would be the first bright band, and this is the second bright band. After the central bright band, what we get is the first dark band and then the second dark band. So we get a central bright band, first dark band, first bright band, and goes on. Similarly, on this side also we get first dark band. So on both the sides of the central bright band, we get dark bands also. This would be the first bright band in the down direction, and this the second bright band in the down direction. So the formula for path difference was delta x is equal to n lambda for bright band, and for dark band the condition was 2n minus 1 lambda by 2. This is called as the condition for dark band. Here n was equal to 0, 1, 2, etc. We'll slightly modify this formula now. We'll write n is equal to 0 plus or minus 1 plus or minus 2 plus or minus 3. For example, we can assume that +1 would mean it is for the first bright band, and +2 would mean for second bright band. Similarly here, n is equal to ±1, ±2, ±3. +1 would mean the first dark band as given here, -1 would mean the first dark band in the down direction. This is what is the equation. Some books will write delta x as equal to 2n plus 1 lambda by 2. Even though this is correct mathematically, this doesn't make sense physically, because in this case n should be equal to 0, but n can't be 0 for a dark band because we don't get a dark central band. Rather, what we get is a bright central band. Hence n is 0 is only for a bright band. So this will not make sense mathematically. This is what we should write. Now here again, the bands have some thickness also. They're not a thin line, they have some thickness as seen here. They have some thickness. In this case, the reference is taken as the center of the central bright band. Keep in mind that the reference would be the center of the central bright band. Now, if you want to find what is the distance of a given bright or dark band, we take the center as the reference and the center of that band as the another line. If I want to find what is the distance between the center bright band and the second dark band, now this would be the first dark band and this the second dark band. The distance from here to here would be the distance of the second dark band from the reference point. So the points we observed here as the bands are not thin, they have some thickness also, and the reference is taken from the center of each band. Now what is surprising here is to observe that the thickness is not uniform. But keep in mind that we'll study later that we have bright band and dark band. It is not that the entire band will be completely bright and this is completely dark. It isn't that way. Rather, what happens is the center of the bright band will have maximum intensity as given here, and when we go away from the center of the bright band, intensity will decrease as seen from here. This center has a maximum intensity. When we go away from it, intensity keeps on decreasing. At some point, intensity becomes 0. So this is taken as the dark band. So there is no clear boundary here. Rather, we take about the centers of the bands. Because it's a misconception that students think that a bright band would have equal intensity everywhere and dark is completely dark. It isn't that way. The brightness would decrease and goes on from here. And also here we define a term called as fringe width. So we'll define something called as fringe. The terms fringe and band are interchanged, but then technically a fringe means it contains one bright band plus one dark band. That's called as fringe. In this case, one fringe here would mean it would be, for example, one bright plus one dark band. To define fringe width, it's called as beta. Beta is called as fringe width. So fringe width is the width of one fringe. Now to define more technically, one fringe, if I draw a bright band, a dark band, and then a bright and dark band, I'm just drawing for sake of understanding it, but the intensity is as given here, not as drawn here, because intensity will vary. Suppose if this is the central bright band, then from here we take the reference as center of it. Now in this case, one fringe would mean it contains one bright band and one dark band. Fringe width means with a one fringe. But to define technically, we take the centers of the bright or dark band. Now for example, if I take this as one reference line, this is center of the dark band. Distance from here to here, we have one more band here like this. Distance from here to here, this would be beta. This would be fringe width. That is because this distance contains one bright and one dark band. That is, it has one bright band here and it has half dark here and half dark here. That's one beta. Similarly, we can find beta from here also. If you look at this distance from here to here, even this also would be beta only because it contains one fringe. There is a complete dark band. There is half a bright and half a bright band here. That's also one fringe width. So books define fringe width technically as the distance between two consecutive bright or a dark band. So this is about Young's experiment and how it was done.